Hello, I'm Giovanni Rodrigues and I'm going to present the paper More Vis, a visual summary for spatial temporal moving regions. With the advance of tracking devices and sensors, datasets of trajectories are becoming prominent. These datasets contain spatial position, generated with two variables, and temporal measurement of the observations. Furthermore, sequences of observations relate to a particular individual, describing its movement through time. Some examples are the data from GPS in smartphones and the measurements of weather conditions, such as trajectories of air masses. Moving entities are often represented as points, dimensionless objects. However, in applications such as climate science and video surveillance, the spatial extent of the observation is vital for analysis. For example, the area coverage of a hurricane or a storm indicates the cities and regions hit by these conditions. The intersection of the bounding box of people in videos represents meetings and interactions. We call the trajectories of objects containing the spatial extent as moving regions. This occurrence region can change according to time and intersect with other objects' regions. How can visualization be used for analyzing moving regions? Common visualizations for trajectories can be adapted for moving regions. Space-Time Cube is an interactive visualization that uses a 3D representation. The space is represented at the cube's base and the time in the cube height. Each can represent the area of the objects and intersections. Dense visualizations create 2D plots. Time is represented in one direction and the 2D space is represented in the other direction. The properties of objects, such as the area, can be represented with the colors. Similarly, storyline visualizations represent temporal data in a 2D figure. The main objective is to represent the interaction between objects through time. Most of storyline visualizations do not consider spatial distances, using an implicit representation of space. However, these techniques present different drawbacks. First, the space-time cube is a 3D object in a 2D screen, and this projection can cause distortions in space and time. It also demands the interaction of the cube to visualize the different points of view. The dense visualizations do not present the trajectories of individual objects and their intersections. Lastly, in storyline visualizations, the representation of distances, areas, and intersections is not straightforward. To address these issues, we propose MoreVis, a summary visualization designed for moving regions. MoreVis is able to represent objects with spatial extent, with their individual trajectories and intersections. The resulting visualization is a 2D plot, with time on the horizontal direction. Each object has its trajectory represented with a curve. The vertical positioning of the curves is based in the original positioning of objects. The weightage of the curves denotes the area of objects' regions, and intersections between curves relate to intersections in the original space. The MoreVis method can be divided into 5 steps. The inputs are the measurements of objects' regions for a sequence of equally spaced time steps. To obtain a 1D representation of the regions, we fit a 2D to 1D projection of all objects and for all time steps simultaneously. This newly generated space considers the distance between different objects and time steps. To perform the projection, it was considered a diverse set of techniques, such as PCA, GSNI, MGS, Hilbert curve, and others. A column is created in the plot for each time step in the data. In each one, the objects are represented as rectangles. These rectangles are initially placed vertically based on the projection value obtained before. The curves represent each object are formed by linking rectangles corresponding to the same objects. The vertical displacement of these curves represents the object's movement, in the original space. The next step is the representation of the areas of objects in the curves. The height of each inner rectangle will be proportional to the area in the original space. Considering that the rectangles are positioned inside the interval 0, 1, we calculate a scaling factor based on the area of objects in the original space, with the intent to avoid larger blank spaces in the plot and also reduce occlusion. After adjusting the heights of the curves, we will update their positioning to represent the intersection of objects better. We employ an optimization algorithm in the vertical position of rectangles with 4 goals. Every intersection in the original space will be represented in the curves. The intersection will have an area at least as big in the original space, but not much bigger. We will minimize the number of spurious intersections in the curves, that is, intersections that are present in the curves but not in the original space. We will minimize the displacement from the original vertical positioning of rectangles. This step contains many details to perform this computation in an efficient manner. First, we divide the optimization in small problems. We separate the problems in each time step and in subgroups of objects that intersect each other. The solution of the problems are combined in the final result. Our formulation also contains a trade-off parameter between the two objectives of minimization. Minimize the extra areas of intersections and minimize the number of spurious intersections. Based on the selected parameter, it is possible to obtain better values for one or the other. Lastly, we mark visual crossings between the curves that do not relate to intersections in the original space. To support and enrich the exploration of more views, a visual interface was designed with 4 views. To present the tool, we will use a dataset of object detection of people in a public area. At the top left, we have the more views view with the main plot. In this example, we see a large green curve. By hovering, the object is displayed in the data view at the top right. It is possible to verify that it is a person coming closer to the camera. We can also identify a group of curves intersecting each other, and when visualizing on the data view, it shows a group of people meeting. It is possible to make a selection in the more views view that will update the intersection view at the bottom right. In this view, a graph containing the intersections of objects of each selected time step is displayed. Lastly, a parallel coordinates plots at the bottom right permits to filter the objects displayed in the more views view. Our tool also presents all interactions between the views to assist analysis. To assess the effectiveness of more views, we perform a set of evaluations. We perform a quantitative evaluation to identify the most suited projection method and evaluate the optimization results. We also perform a qualitative evaluation to verify the visual representation of basic patterns in a simple dataset and compare it with reference visualizations. Morvis was able to present all intersections, avoiding the spurious intersections at most, a problem of related techniques. A user study with 9 participants was also performed to assess the effectiveness of your visualization in analytical tasks. Most users agreed with the effectiveness and easiness of Morvis, and also agreed that the extra views in the interface helped in the analysis. One participant commented, Morvis helps to visualize information that would be very chaotic with the data view alone. Our evaluation also presented other experiments and use scenarios. More details are presented at the paper. Despite the use of the optimization technique, it is not always possible to fully represent intersections from 2D to 1D. Some situations will have missing or rest intersections. Our technique guarantees no missing intersections, with minimal est intersections. They can also be verified in the intersection view. Our solution solves a mixed-edge integer program for each time step, which is computationally expensive. This can be overcome by processing the optimization or analyzing subsets of the data. In future works, we want to consider other types of datasets, such as clusters of trajectory data or trajectories with uncertainty. Thanks for the attention.